Okay, continuing with our examples with partial fractions, it's important to understand that when there is a multiplicity greater than 1 for any of the roots of the denominator, you must consider the different cases in which your root could have been used. So suppose that we were asked to find the decomposition of 2x minus 5 over x cubed minus x squared. We must recognize that that root x equals 0 has a multiplicity of 2. So we would write this as three possible terms. Three possible terms. That we have a over x squared as a possible term, b over x as a possible term, and then a third term, c over x minus 1. Those are the possibilities that I would have for my terms that could be combined with that common denominator of x cubed minus x squared. So if we want to determine the values a, b, and c satisfying this identity, we can multiply both sides of our equation by our common denominator. And that common denominator is x squared times x minus 1. So we would be able to say that 2x minus 5 must be equal to a times x minus 1 plus b times x minus 1, and then plus c times x squared, right? That this c term would need to be multiplied by x squared over x squared, right? This b term would need to be multiplied by x and by x minus 1 in numerator and denominator, right? And then this a term would need to be multiplied by x minus 1 over x minus 1, so I'd have this common denominator. So if I come through here, we're going to see an issue that arises when we have this multiplicity greater than 1. Because over here, if we say if x equals 1, right? So if x equals 1, we're going to have 2 minus 5 being equal to a times 0 plus b times 0 plus c times 1. And so therefore we would know that, hey, c is going to be negative 3. Okay. Similarly, all right, now I kind of gave that away on what the values are they're going to be, and you can check with Wolfram Alpha. But similarly, we can come over here and say, okay, well, what about if we do our work and we say, well, what if x is equal to 0? Well, if x is equal to 0, we're going to have negative 5, right? Because 2 times 0 is 0. So negative 5 being equal to a times negative 1 plus b times 0 plus c times 0. So that means then that a must equal 5. And so we see, hey, we got c is negative 3 and a is equal to 5. But this cover-up method that we're using can't be the only method to use when we have this multiplicity greater than 1. We also have to be able to do this idea that is called equating coefficients. So what do we mean by equating coefficients? We mean the following, right? That the left side of our equation is 2x minus 5. The right side of our equation could be written as ax minus a plus bx squared minus bx plus cx squared, right? Which then I could write as x squared times c minus b plus x times a minus b, and then what would we have? Minus a. Okay, well, if we equate coefficients, that tells us that negative 5, the constant, must be equal to negative a. It also tells us that 2, the linear coefficient, must be equal to a minus b. And as well, it tells us 0, right, because there's an implied 0x squared over here, that 0 must be equal to c minus b because there is 0x squared, right? The coefficient of x squared would be 0. Well, if 0 is equal to c minus b and c is equal to negative 3, well, then b has to be equal to positive 3. So what does that mean? 2x minus 5 all over x squared minus, or x squared times x minus 1 can be written as 5 over x squared plus 3 over x minus 3 over x minus 1. And that would be our partial fraction decomposition. Once again, this approach is going to be very, very useful when you do the work in calculus dealing with some integration techniques. Okay, so check your work using different resources, right? Wolfram Alpha is very, very useful resource. Okay, so let's look at one more here. Express this in partial fractions. Why don't you pause the video and see if you're able to do the work, and unpause the video to check your answers. Okay, so our first step with partial fractions is to consider, right, what the factored form of the denominator is, and that would be in this case x plus 3 times x plus 2. And so we're going to consider our possible terms that when combined would get us this single fraction. So we have a over x plus 3 plus b over x plus 2. If we multiply both sides of our equation by our common denominator, if we do that, we're going to have a times x plus 2 plus b times x plus 3 must be equal to 1. Okay. Then I'll go ahead and talk this solution using the two methods, right? So I'll talk about using our cover-up method, right? Sometimes known as the Heaviside cover-up method after an English mathematician. And we'll also talk about the method of equating coefficients. Okay. So the Heaviside cover-up method is the method that we discussed in previous videos, which is to select values that will allow you to simplify your computation. So if x is negative 2, then we know b is equal to 1. And if x is negative 3, right, then we know negative a is equal to 1. And so then we have our solutions, right? That means that our partial fraction decomposition is going to be 1 over x plus 2 and then minus 1 over x plus 3. Okay. What would be this method of equating coefficients? Well, the method of equating coefficients would be able to say, hey, on the left side of our equation, we have x times a plus b. And we also have our constant of 2a plus 3b, right? And that must equal 1. So therefore, a plus b must be equal to 0 because on the left side it's our linear coefficient and there's no linear term on the right side. And 2a plus 3b is the constant and that must be equal to 1. So now we have two equations and two unknowns. If we multiply our first equation by 2, we'll multiply both sides of our first equation by 2, then we have 2a minus 2a, which would be 0a. We'd have 2b minus 3b, which would be negative b. And we'd have 2 times 0, which is 0, minus 1, right, which would be negative 1, and that would imply that b is equal to 1. And if a plus b is equal to 0, right, then we know that a must be equal to negative 1. So either way works, whether you want to use this Heaviside cover-up method or you want to use the method of equating coefficients. Thank you very much for your time. We'll have one more video with partial fractions if you need to see some additional examples.